Now I've got the same circuit, but this time I am not faffing about with LEDs. What I'm doing now is I've put various meters in the circuit and labelled the circuit with collector current IC, base current IB. I can switch the transistor on and off, so there is no current flowing there, no current flowing there, and therefore no current flowing there. When I switch on, notice that nearly 6 milliamps there added to half a milliamp. I'm sorry about the units, Crocodile Technology does this daft thing. That is 0.5 of a milliamp. If I add that and that, I get that. So my useful equation is that IE, the emitter current, always equals the collector current and the base current. You should have no surprises there. That is Kirchhoff's first law. The current entering a junction is the same as the current leaving. Only this junction here is the transistor. So the current on the collector side added to the base current equals the total current. If the current is sufficient, the transistor will conduct. Okay? Now, if we measure voltages, the red flags indicate voltage. I've got a supply of 6 volts there, 6 volts there, 6 volts there, 6 volts there. Because current can't flow, the voltage there is no volts. So everything on the output side until it's switched on is at the voltage of the supply, 6. When I switch the transistor on, my 0.6 volts, 0.67 to be precise there, 678 millivolts, makes the transistor conduct, and the voltage there becomes 0. Or it's near damn it 0, 34 millivolts. 0 volts on the emitter side. Now, in electronics, power is current times voltage. I'm not going to go up and down with the blind thing. So power is current times voltage. And if you look at the bottom line, I've put power dissipation. Power equals the collector emitter voltage, which is 0, multiplied by the current, which is 6 milliamps. Right, if you multiply a number by 0, what's the answer? 0. So our transistor, when it's conducting, is dissipating no power. So when it's acting as a switch on, there's no power. When I turn the transistor off, the current flowing through it is 0, even though the voltage arriving at it is 6. 6 times 0 is 0. So when a transistor is off, there's no power. That's rather useful. When it's off, there's no power. When it's fully on, there's no power. So you can switch big currents with a transistor and get no or negligible power loss. When you do your investigation on Monday or Tuesday, I will ask you to put your finger, you won't hurt yourself, on the transistor case to prove that when it's fully on, it's not getting warm, and when it's fully off, it's not getting warm. But halfway, it will be getting warm because there'll be some voltage and some current. So let me just go through that as a rehearsal again. When it's on, there's a current flowing through there, but there's no voltage across it. Between there and there, the voltage is almost 0. Anything multiplied by 0 is nothing. So switch on, when it's conducting, the power loss in the transistor is negligible. we regard it as zero, as a compromise, and that's what I've put in that bottom equation. When it's off, because there is no voltage across it, no current, it's also off, no power. Let's go a bit further.